Hello everyone, I am LIYANAWADUGE from Department of Electrical and Information Engineering, University of Rohtak. So, this video presents my machine learning module project on human activity detection. As engineers, we are interested in how technology can monitor human movement for applications in rehabilitation, elderly care, and sports medicine. This project is a perfect example of using AI to understand human biomechanics. Okay, why is human activity detection important in biomedical engineering? First one is rehabilitation monitoring, that is known as track patient progress after injuries or surgeries. So let's go to the fall detection or elderly. So we can use gyroscope sensors automatically alert caregivers. Physical therapy assessment, that is quantify movement quality. Sports performance analysis, that helps athletes optimize their training. This project bridges signal processing, machine learning, biomedical engineering applications. Exactly what we learn in our machine learning stream module. So, the datasets contains accelerometer readings from 5 sensors placed on the body. Each sensor measures acceleration in X, Y, and Z axis, just like the inertial sensors we study in our biomedical instrumentation course in machine learning. So in clinical settings, similar sensors are used for gait analysis in Parkinson's patients, movement assessment after stroke, prosthetic limb control. The data was collected at 40 Hz, which is sufficient for capturing human movement. Since most activities have frequencies below 20 Hz, according to the Nyquist theorem, we learned in signals and systems in our second year. So, human activities are not single snapshots, they are sequences of movement. Think about the squat, it has downward face, hold, and upward face. I created overlapping windows of 20 time steps with 50% overlap. This is similar to how we analyze ECG or EEG signals in biomedical signal processing using windowing techniques to capture temporal patterns. The overlapping ensures we don't make mistakes or transitions between activities, which is crucial for continuous monitoring applications like 24-hour patient activity tracking. Let's go to the machine learning theorem, machine learning algorithms. So, we have built such a system with Jupyter Notebook. I have now loaded them. So you can see that for the model I chose the CNN LSTM hybrid architecture. Let me explain why this makes sense from a biomedical perspective. CNN layers act like feature extractions. Convolutional neural networks, they learn to recognize specific movement patterns, just like how clinicians recognize gait abnormalities. LSTM layers capture the temporal dynamics, the sequence of movements over time, similar to how we analyze time series medical data like ECG or EMG or EEG. The model has 3 CNN layers, 64, 128 and 128 filters. So, followed by an LSTM layer with 64 units. This architecture is actually very similar to models used for EEG signal classification in brain-computer interfaces. Let's go to the training results. After watching this, you can see I have included the libraries first, then I have called the datasets, and first I have classified them into 6 branches. So then I go to the dataset and import the dataset as CSV files. So then I read them. So you can see loaded successfully again. Then I'm going to the loading data files. I have loaded cycling, push up, run, likewise. So this is just this is the basic of the dataset. So if we go to the next cell, overlap ratio is 0.5. So you can see label method. So I have labeled cycle, cycling, push up, run, square, table tennis, walk. So I have created sequences. You can see that the cycling and push up and run, how they are processing. After that we can see the processing graphs. So you can see cycling sample sequence, push up sample sequence, run sample sequence, squat sample sequence, table tennis sample sequence, walk sample sequence. Walk. So you can see the X shape and Y shape with this using these functions. So let's go to the scale and scikit-learn model I have implemented by importing train test split. So you can see that I'm going to the okay, let's go to the code. So now let me explain the machine learning algorithms and techniques I have used in this project. As engineers, understanding these algorithms helps us to choose the right tool for clinical applications. So first one, I have used supervised learning approach. This is a supervised learning problem. We have labeled data where each sequence is tagged with the correct activity. The model learns to map sensor readings of activities. Also, similar to how a medical student, I learned to correlate symptoms with diseases. So why did we use deep learning? Traditional ML algorithm like random forest or SVM would require manual feature engineering. Someone would have to manually calculate things like mean, variance or frequency features like from data. So but with deep learning, the model automatically learns the relevant features from raw data. This is especially useful in biomedical applications where we might not know ahead of time which features are most important for diagnosing a condition. The model I chose is CNN LSTM hybrid. As I mentioned before, this combines two powerful neural network architectures. First one is convolution neural networks. CNNs are typically used for image processing, but they are excellent at finding local patterns in any kind of grid-like data. In our case, each 1D CNN layer slides a small window across the 15 sensor readings. It learns to detect specific patterns like the characteristic spike when a foot hits the ground during walking. Multiple CNN layers stack to learn hierarchical features for simple edges to complex movement patterns. Think of it like how a clinician first notices individual symptoms, then combines them to recognize a syndrome. So, long short-term memory, then, that we known as LSTM, are especially type of recurrent neural network designed to remember information over long sequences. They solve the vanishing gradient problem of traditional RNNs. Key components of a LSTM cell. First one is forget gate that decides what information to discard. Second one is input gate that decides what we new information to store. Third one is output gate, decides what to output at each step. In our application, the LSTM captures the temporal dynamics, the order and timing of movements. For example, a squat has a specific sequence, descent, pause and ascent. The LSTM learns this temporal pattern. Why we combine CNN and LSTM? The CNN LSTM hybrid gives us the best of both worlds. So, if we consider CNN, it acts as a feature extraction. Its analogies identify individual symptoms. If we consider LSTM, it acts as a temporal modeling. The analogy is understanding disease progression. In biomedical terms, CNN detects what movement is happening each movement. LSTM understands how the movement evolves over time. This is similar to how an EEG seizure detector might use CNN to identify spike patterns and LSTM to understand their evolution over time. So, if you go to the training graphs, you can see the training. At initial step, it has accuracy of 0.8144. So, training samples are 11,858. Validation samples are 2,541. Batch size is 32. I have used 100 epochs. You can see how that is trained. So after 50 epochs, you can see the accuracy is 1.0000, loss is 1.59, and multiply 10 in 10 to the power minus 4. So at epoch 51, early stopping, restoring model weights from the end of the best epoch. So training completed. But if we consider the plot training history, you can see that the model accuracy is nearly like a line, linear. So model loss is very largely decreasing. And also class distribution, cycling, push-up, run, squat, table tennis, ball. You can see absolutely for early stopping, as I mentioned before, monitors validation loss and stops training when it stops improving, prevents overfitting. Dropout randomly drops 20 to 30% of neurons during training. Act as regularization. Batch normalization. Normalization layer inputs speeds up training and provides some regularization. Adam optimizer. Adaptive learning rate optimization converges faster than traditional SGD. These techniques ensure the model generalizes well to know unseen data, crucial for clinical deployment, where patient data will differ from training data. So, if we go to the neural network, I have made it using Python. I will send the thing what I have added. So this video you can see that our neural network diagram. You can see for sensor data, going to feature extraction, CNN, and temporal modeling, LSTM, STM64. So you can see that input is like this: convolution 1D, batch normal 1, convolution 1D, batch normal 2, convolution 1D, batch normal 3. After that, LSTM64, go to dense 64, dense 32, finally goes to output 6 classes. Okay, that is about the thing. So if you go to the training validation, you can see that to evaluate the model, I use multiple metrics: accuracy, overall correctness. Finally, I had 100% accuracy. Precision when it predicts an activity, how often is it correct? Recall, what percentage of actual activities did it catch? 99.97%. Phi score, you can see that harmonic mean of precision and recall, 99.90%. Confusion matrix, you can see that which activities get confused. Also, you can see normalized confusion matrix. In medical applications, recall might be more important than precision. We would rather have false alarms than miss a real fail. So, sense analysis technique. For the bonus task, I use a feature ablation study, systematically removing sensors to see their contribution. This technique tests all possible sensor combinations, 31 combinations, trains a smaller model for each combination, compares performance. This is valuable for wearable design. We can identify the minimum number of sensors needed for acceptable accuracy, making devices more comfortable and affordable. You can see that in this. In this, you can see the results. Testing combinations of one sensor. It shows that 96.14%. For this whole system, this whole bonus task, I have spent rather than more than 30 minutes only for this one. So you can see the combination of two sensors, 1 2 3 4 sensors, 2 3 4 0 1 2 3 4 0 2 4. Likewise, you can see the testing combinations and evaluating performance. So performance of different sensor combinations, you can see that. Then I have saved the model with H5 extension, and also I have saved the scalar using Jobly pickle file. So in JSON file, I have saved as class mapping.json. Again, we have JSON file, that is model architecture.json. So if we configure K, stride, overlap ratio, sensors axis, total features, activities, num classes, test accuracy, final value accuracy. So you can see that model saved as human active model final.h5. So best model. So for Hugging Face deployment, I have used before that. Now let me dive into the machine learning algorithms and techniques I used. As biomedical engineering students specialized in electrical engineering, understanding these help us choose the right tool for clinical problems. This is a supervised learning problem. We have a labeled data where each sequence is tagged with the correct activity. The model learns to map sensor readings to activities, similar to how a medical student learns to correlate symptoms with diseases. Okay. And let's go to the application I have made. This application, you can see that we have CSV upload facility, also manual sliders. You can change the each sensors readings manual. If we attach this to a real-time model, we want to have a Raspberry Pi for implementing this ML algorithm, and afterwards we can play with the real data. This is just the real data we have downloaded. So we can play with the real data. If we want to play with the real data, we have to find Raspberry Pi or similar, but similar controller, or I mean the computer, which can have ML algorithms in that. You can see if we change the sides in these frames, I haven't filled yet. I fill now. See that we can use a slider. It's very easy to deploy. This is my Hugging Face application. I will add them to my YouTube channel, and if we detect, you can see this symptom is table tennis. It has 100% sure, and that means probability, that it says that it combinations has happened by table tennis playing. So you can see that. So, and finally I should say that I should be thankful to our supervisor Dr. Subodha Gunawardhane, and I request your question and answer your questions in the YouTube channel. So you can ask any question and I will answer that. So thank you for hearing me, listening to me. Thank you so much and goodbye.